Welcome to Networks Professionals.
So think for a second about the sheer number of devices connected to your Wi-Fi right now. Your laptop, your phone, maybe a smart TV, a tablet. All of these isolated, private devices are just constantly firing off requests. But have you ever stopped to wonder how they actually manage to communicate with the vast, totally chaotic public web? I mean, how does a request from your specific phone travel out into the world, grab a web page, and find its way back to your exact screen without getting lost in the billions of other connections? Well, welcome to this explainer. Today, we're going to completely unpack the brilliant piece of technology that makes all of this seamless communication possible: Network Address Translation, or NAT for short. Think of NAT as the ultimate, hyper-efficient digital mailroom powering your daily web browsing. Honestly, without it, our modern internet experience would literally grind to a halt. We're going to break down exactly how this digital mailroom sorts, translates, and delivers every single piece of data you request. Section 1, the private web divide. So, to really understand why NAT is so critical, we first need to look at the core conflict here, which is that our local devices are speaking a language the outside world simply cannot route. Okay, let's dive into this. There's a really rigid boundary between your local network and the outside world. On one side, you've got your private IP address. This is the local identifier your router gives your device. The catch? Private IP addresses are completely unroutable on the public web. If your laptop tried to ask a web server for data using its private IP, the internet wouldn't have a clue where to send the response back. It's kind of like trying to receive global mail by just writing bedroom 2 on the envelope. It doesn't work. On the other side, we have the public IP address. This is the globally unique, fully routable address your internet service provider assigns to your whole network. Because your private IPs literally cannot survive out there on the public web, a translator becomes absolutely necessary to bridge that gap. Section 2, how NAT actually works. Now, I want to deliberately slow down the pacing right here, because we're going to follow what I like to call the hero's journey of a single data packet. Let's walk through the router's 4-step mailroom process as this packet leaves your device, ventures out, and returns safely. Step 1 is the request. Let's say a device on your private network, we'll call its private IP 192.168.1.5, wants to load a web page. It sends a data packet to the router with that private IP listed as the source. Step 2 is the translation. The router intercepts this packet right before it hits the internet. It strips away the unroutable private IP. Actually, scratch that, it replaces it by rewriting the source IP to its own routable public IP address. Let's say 203.0.131.5. Step 3 is tracking, where the router meticulously logs exactly what it just did. And finally, step 4 is the response. When the destination web server replies, it sends the data back to that public IP. The router receives it, figures out who originally asked for it, translates the destination back to the private IP, and boom, delivers the data straight to your screen. Now, what's really interesting about this slide is the mechanism that makes all this tracking possible: the NAT table. The NAT table is essentially the router's secret ledger. When the router swaps your private IP for the public IP, it creates a temporary record of this exact translation right here in the table. This is the sole reason why, when the returning data hits your router, it doesn't accidentally end up on your roommate's laptop or your smart TV. The router just checks the ledger, finds the exact translation it made milliseconds earlier, and ensures the data finds its way back to your exact device. It's absolutely brilliant. Section 3, 3 types of translation. All right, let's pick the energy back up for a quick fire round, because routers use a few different flavors of translation depending on the network's exact needs. The first one, and honestly by far the most crucial for our daily lives, is PAT, Port Address Translation. You'll also hear it called NAT overload. PAT is the absolute heavy lifter for modern networks. Instead of just swapping IP addresses, PAT assigns unique port numbers for each connection. This means multiple private IP addresses can all be mapped to one single public IP at the exact same time, separated simply by those unique port numbers. And this brilliantly illustrates the one-to-many setup. Imagine a single public IP address acting as a VIP bouncer for a crowded club. You've got dozens of devices inside your house: phones, laptops, gaming consoles, and they all want to get out onto the internet. Instead of needing a unique public IP for every single device, PAT allows that one single public IP address to successfully act as that VIP bouncer, managing and translating for many different private IP addresses simultaneously. It's just incredibly efficient. But what if you don't want a one-to-many setup? Well, that brings us to static NAT. Let's quickly contrast PAT with this method. Static NAT creates a permanent, fixed one-to-one mapping between a specific private IP and a specific public IP. It doesn't change, and it definitely doesn't share. This strict one-to-one mapping is typically reserved for times when you're hosting a public-facing server, like a web server or an email server, right on your local network. The outside world always needs to know exactly where to find that server, so a permanent translation is perfectly suited for the job. Finally, to round out the categories, we have dynamic NAT. This one kind of sits somewhere between the other two. Dynamic NAT maps private IP addresses to a temporary, predefined pool of public IPs. It basically operates on a super simple, first-come, first-served basis. If your device wants to go online, the router grabs an available public IP from its pool and temporarily assigns it to you. When you're done, that public IP goes right back into the pool for the next device to use. Wow, okay. We've covered a lot of ground today, from the basic packet journey to the real intricacies of PAT and static mapping. If you're an eager learner ready to take a deeper dive into the exact routing rules, the command lines, and the intricate network configurations that make all this happen, I highly recommend checking out Cisco's NAT documentation. It is incredibly comprehensive. And also, Fortinet's cybersecurity glossary is fantastic for breaking down how these concepts apply to modern security. As we wrap up this explainer, I want to leave you with a final, provocative thought to consider. By masking our private, unroutable IP addresses from the massive public web, NAT doesn't just act as a translator. It essentially acts as an invisible shield for our local networks. But what happens to our network security when those fundamental translation rules change, or when those strict mappings are somehow bypassed? It's a truly fascinating layer of cybersecurity, and I really hope this deep dive encourages you to keep questioning and exploring the invisible infrastructure that connects us all, long after this explainer ends. Keep learning, and I'll catch you next time.
Thanks for watching.